adding in two bias terms here. I didn't add them before just for clarity, but I'll show you when we add those in. It's easier to write out equations without a bias. It's easier to tell what's going on. Okay, so I'm going to go ahead and create a NumPy array called outputs just to store the outputs at each sequence position. I'm going to create a NumPy array called hiddens to store the hiddens at each step. And this is for use in both passing values back and forth and in back propagation, which we'll get to in a bit. We'll set our previous hidden to none, and then we will pull out the sequence that we had before. All right. And then we very commonly write RNN forward and backward passes in terms of a for loop. So we're just going to say for I in range 3. 3 is the length of our sequence. We're first going to get our input X. So that is the sequence element at index I. We're just going to reshape it into a 1-by-1 matrix. Then we calculate Xi, which is just I times our input weight. Then we check to see if this is the first item in the sequence or not. If it's the first item in the sequence, we don't have a previous hidden state. So we'll say if previous hidden is none, our XH just equals Xi. Otherwise, our XH equals Xi plus our previous hidden state times our H weight plus our H bias. So this is where we add in our hidden bias. The bias term just does basically a constant shift of each value. So we're just adding it in. Then we apply our nonlinear activation function, in this case, the hyperbolic tangent, and we set our previous hidden to XH. And then we store our hidden for use in back propagation later. And then we can define our output. So our output is XH times our output weight plus our output bias. And then we can store our output into our outputs array. So this is the same thing we just did manually, step by step up here. It just is in a for loop so that we don't need to write out all of the code. All right, so we can run this and we can check our network outputs. So we can see that the use of the hyperbolic tangent activation function instead of ReLU makes these values a lot nicer. And we can also look at the hiddens and we can see that they're not going crazy, right? They're staying about the same size over time, which is what we want. Okay, so that's a full forward pass of an RNN. Let me pause and check QA. How long is this webinar? This should be another half hour. I have to go through the backward pass. Can we access the previous lessons if we did not attend them? Yes, you absolutely can. So I shared a link to the full curriculum of this series, and there's write-ups for each of the lessons. I'm working on fully recording all of the videos, and I'll have those up as well. I'm afraid I can't answer off-topic questions. There's not a ton of time. Okay, folks, so that is our forward pass. Now it's time to think about our backward pass. And the backward pass of a neural network is when we update the parameters, the weights and biases, to reduce our training error. So we first want to figure out our error. So in this case, we're going to use mean squared error, which is the same thing we used in previous lessons. And we essentially want to figure out, how do I need to adjust each of the parameters in my network to reduce error? Now, this is a lot more complicated in an RNN than in a regular neural network, and I'll show you why. So in an RNN, so this last output here, output 3, only depends on the previous hidden step, right? H3. So H3 here passes data into output 3. So if we're going to find the gradient of H3, we would only need to look at the gradient against output 3. So we would need to say, okay, what's the error in this output? Now I can go adjust my parameters based on that. But for the inside steps, so H1 and H2, it's a little bit different. So you can see that H2 passes its output in two directions. So H2 actually affects O2 and O3. So we need to actually use both gradients to adjust the H2 parameters. So a gradient is just the partial derivative of our loss with respect to a parameter. So what we need to figure out is, how do I change H2? But when we change H2, or sorry, how do I change the weights in the H2 step? But when we change the weights in the H2 step, we're changing both output 2 and output 3. So we need to figure out a way to account for that. And I'll show you how to account for that. All right, so first, we're just going to grab our mean squared error and mean squared error gradient function. And then let's say these are our actual temperature values. So let's say there's 70, 62, and 65. And then we can create our loss gradient based on our MSE gradient function. If you don't know what the MSE gradient function is, I talked about it in the neural network lesson. All right, so I'm going to calculate my gradient by taking my actuals and my outputs. So this essentially tells us how much do we need to adjust the output of the neural network to reduce our error. And then we can take a look at our loss gradient. Okay, so this is our gradient at each sequence position, right? Sequence time step 0, time step 1, time step 2. All right, now we need to figure out the backward pass. And I'm going to put up a diagram. It's going to look a little crazy, but I'll talk you through it. Okay, so what I just showed you is our loss. It's our mean squared error. And that gives us basically our gradient against our network output. It tells us how much do I need to adjust the output of the network to reduce my loss. Now we can feed that output gradient to calculate our output weight updates. So how much we need to update our output weights. And that's just the input to our output step, which is the output of the hidden step, transposed times the output gradient. Then we need to calculate our gradient with respect to the previous step, the hidden step. So we take our output gradient and we multiply it by the output weights, but transposed. So this is the exact same thing you would do in just a regular feed-forward neural network. The exact same way you calculate the weight updates and pass the gradient to the previous layer. The complicated part is here. This is when you calculate the gradient against the hidden weights and pass the gradient down to calculate the gradient versus the input weights. So we need to take the derivative of our hyperbolic tangent function and multiply it by the inputs to this. So the inputs to this are the gradient at the next step, because remember, the current hidden step impacts both the next output and the current output, and really all future outputs, right? So we're going to pull back the gradient from the next step and combine it with the gradient from the output, and use that to update our hidden weights and our input weights. And we're also going to pass the gradient from this step to the previous step. All right, this seems a little bit crazy now, but it'll get a little bit simpler once I code it up. So let me show you what this looks like. So this time we're going to loop backwards from our last sequence position to our first sequence position. So we're going to keep track of, instead of the previous hidden state, we're going to keep track of the next hidden state. And we're going to define our gradients. And we'll define our I weight grad. And we'll do 0 times 5. So this will basically set each of our starting gradients to 0. And we want to add up our gradients across every sequence position. So we're essentially going to keep adding to these lists to create our final gradients. Okay, so we're going to say for I in range 2, so starting at our last sequence position and stepping backwards until the first sequence position. We're going to get our loss gradient, which is just our loss grad at that position reshaped. So you'll remember we had our loss grad up here. So it's just going to grab at each sequence position basically how far our prediction was from the actual value. All right, then we're going to calculate our output weight gradient, which is just going to be our input to our output step, which is the output of the hidden step at that sequence position, but transposed. So we're going to use numpy.newAxis to transpose this. So it goes from a 1x2 or 1x5 or whatever matrix to a 2x1 or 2x5 matrix. And that's what we need to do to correctly calculate the gradient. I explained this in the previous neural network lesson. If you want to read through that to understand why we transpose. All right, so we're basically taking to the output step and then multiplying by the gradient to figure out how much we need to adjust each of our output weights. So that's what we're doing at this step. That's this part of the diagram, the xht1.t at OG. All right, then we're going to calculate the gradient against our bias. And this is just the mean of our loss gradient. The bias is directly added in the forward pass to our output, or it's over here. So what we need to do is when we change the bias, it directly changes the network output. So we can just reflect that by taking the mean of our loss gradient. Okay, now we need to find the gradient with respect to the previous layer's output. So that is our loss gradient times the output weight transposed. So this basically tells us my hidden step output some value. How much do I need to adjust those values to reduce error in the output? So that's what this ograd tells us. It's essentially doing this thing right here, where we're passing our values into the previous hidden step. Okay, and then what we'll say if we're starting at the last sequence position, so there is no next hidden state. So we'll say if next hidden is none, hgrad equals ograd. So you see in this tan h derivative, we're adding in the gradient that's coming from the output to the gradient coming from the next hidden state. But we can't do that here because there is no next hidden state. If not, what we do is we take our next gradient, so the gradient from the next hidden state, we multiply it by the hidden weights. Because in the forward pass, when we passed our hidden state to the next layer multiplied it by h weight. So we essentially need to undo this multiplication. All right, so we're going to say our hgrad equals ograd plus next hidden. So that's the gradient in our next hidden position times hweight.t. All right, so this gives us our full gradient with respect to the output of the hidden step. But you'll remember in the hidden step, we do the hyperbolic tangent. So we need to undo the hyperbolic tangent. So we'll take our tan h derivative, which is just 1 minus. This is why we stored our output in the hidden step. So that's the derivative of the hyperbolic tangent function. So we're taking in the forward pass when we stored our hidden value, we're taking this and getting the derivative. So we can essentially undo when we did this the hyperbolic tangent. So undo it on the gradient. So then we're going to say our hgrad equals np.multiply hgrad and our tan h deriv. Okay, let me go through this again and explain it one more time, because it is a lot. This is pretty complicated. I mean, I wouldn't really expect anyone to get it the first time they hear about it. It takes some time really thinking about how these operations work. So no worries if you're not immediately getting this. It takes a while. Okay, so we're first taking our loss gradient and we're grabbing the gradient corresponding to our sequence position. So in the forward pass, our network output a prediction. We're basically saying how right or wrong was that prediction. Then based on how right or wrong our prediction was, we're adjusting our output weights. So we're saying, okay, how much do I need to adjust my output weights to make my prediction better? And we're adjusting our output bias. Then we're taking the output and we're saying, okay, I took this output in the forward pass from the previous layer, then I multiplied it by the output weight. So we're essentially undoing that. We're reversing the multiplication so that we can pull our gradient down to the hidden step. Then what we're saying is my gradient was sent in two directions. Or sorry, my output in the forward pass was sent in two directions. It was both sent to the next hidden state and to the current output state. So we add together the gradients coming from both sides. We add together the output gradient with the gradient from the next hidden state. But in the next hidden state, our whatever output we sent was also multiplied by the hidden weight. So we basically undo that multiplication so we can pull the gradient across to our current hidden step. Then in the forward pass, we applied our hyperbolic tangent. So we essentially undo that hyperbolic tangent on the gradient. So we get gradient values inside the hyperbolic tangent. Okay, and then at this point, we store our hgrad as part of our next hidden state. Okay, and then if I is greater than 0, we are going to update our hidden weight. So that is that's this piece. We're computing our gradient with respect to our hidden weights. So we're going to say our h weight grad plus equals hiddens I minus 1, because the input to our hidden step was the output of the previous hidden layer in the forward pass. Okay. And I'm using this np.new axis to basically do a transpose in this case. So it's transposing the hiddens. So in the diagram, you'll see .t for transpose. Here, I'm just using a new axis because it takes a little less code in this particular case to do that. Okay, so that's the gradient with respect to our hidden weights. Then we can do the same thing with our bias. And then we can do the same thing with our inputs. So that's this piece where we're calculating the input weight gradient. So we take our input sequence at this position. So that would just be sequence I. And we transpose it. And we multiply it by our hgrad. Okay, so this gives us how much we need to update each of the parameters in our network to reduce error. I'll go through this last piece that I just wrote again. All right, so we have the gradient with respect to the output of our hidden step. That's hgrad. Then we're going to pull it across our nonlinear activation function by undoing what we did in the forward pass. Then we're going to calculate our gradient against our hidden weights by essentially multiplying the input in the forward pass. So here, let me go back up to my forward pass. This part is a little complicated, so I'm going to talk about it. In the forward pass, here's the forward pass. So we took our input x, we multiplied it by wi to get xi, x times wi. Then we also took the previous hidden step and we multiplied it by wh to get xh. And then we applied our hyperbolic tangent function over xh plus xi to get the output of our hidden step. So we essentially take the gradient from here and we feed it here and here to calculate the gradients against against wh and wi. All right, so this is us calculating the gradient against wh. So it's taking the input from the forward pass and multiplying it by the gradient, and the input the input that was multiplied by wh, and this is doing the same thing with the input that was multiplied by wi. Okay, so those are our gradients. And we can take a look at the end to see what we have. So these are the gradients with respect to our sequence parameters. Okay, let me pause here and just take questions. That was the most complicated part of an RNN, and really the most complicated part of any neural network is the backpropagation step. So if you are not getting it immediately, do not fear. Almost nobody does. I use a tool called Excalidraw for these illustrations. Can I use this same method for any sequential data that is numeric? Yes. And the very cool thing is you can use this for any sequential data, even if it's not numeric. So RNNs are very commonly used for working with text. So in NLP. So you essentially convert the text to numbers, and then you feed those numbers into an RNN. And RNNs can actually predict what word will come after or what sentence will come after the input. So they've been used for things like translation. You could build something like GPT with an RNN, although it wouldn't be as good because GPTs use transformer models, which I'll actually talk about in one of the next webinars. All right, folks, I think that's all the questions. Okay, and then the final thing we have to do here is update our parameters using our learning rate. So this is what we did in our previous neural network tutorial. So we essentially just take our gradients, multiply them by the learning rate, and subtract them from our original parameters. I won't make you watch me type out each single update, but we can update all of our parameters the same way. And what we end up with is our new sets of input weights, hidden weights, etc. Okay, so that's a full forward and backward pass of an RNN. I don't have enough time to show you how we pull it all together and actually run this over our whole data set, but I will take questions. If you have any questions, I know you probably have a lot. What if you wanted to predict the comments of a respondent by their respondent ID? Anna, it depends what you mean by predict. Like, do you want to actually generate their comments, or do you want to predict if they made a specific comment? If they made a specific comment, yeah, you can do that. You would essentially feed in the whole sequence, and you would use the last output of the sequence as your prediction for respondent ID. Okay. Any questions at all? Okay, let me share the links again to the notebooks. They're all the way at the top. Here they are. And you can also see previous. So in the first link, you can see all of the lessons that are done so far. So you can see the previous lessons as well. In the second link is for the current lesson. All right, folks, if you're raising your hands, I can't actually see who's doing that or see what questions you have. So please put your questions in Q&A. That's where I can answer them. Okay, since we have a few extra minutes, I can just copy and paste in some of the code for training the full network. I won't have time to really explain it or do it line by line, but at least you can see what it looks like. So this is the code to process our data and split it up into training, validation, and test sets. We use the training set to actually train our network. Then we need a function to initialize our parameters. So we initialize our weights, our input, hidden, and output parameters, weights and biases. Then we do the forward pass. This is essentially the same thing that we already did. It's just wrapping it up and making it run a little bit better. That's our forward pass. And then we have our backward pass. Same thing we already did. And it's a lot of code, so I can't explain it all, sadly. And then we can actually write what's called a training loop to loop over our input data, process it, make predictions, and then compute our gradients and update our parameters. And we can monitor how our network does. I've set a very low learning rate, so the network has really high error initially, but it descends and eventually has the same performance as actually the PyTorch RNN implementation, as far as I can tell. So we can take a look at how this trains epoch by epoch, and we can see that come out. Okay, folks. Well, this is the end of the webinar. I see a question. Can RNN be used for text to image, or is it just stable diffusion applicable? You can use an RNN for text to image. You can make it generative. I would not recommend it, though. I would recommend using transformers, which are a newer model that I'll talk about later. You can definitely use RNNs to predict sentiment, for sure. Okay, and we can see as our network processes the input data more and more times, so each epoch is essentially one trip through our input data, we can see that our error is getting lower on both our training and validation sets, which is what you want to see. Okay, folks. Well, I think that's everything. So thanks a lot for attending. I'm doing a whole series on how to get from zero to building a GPT model. So stay tuned for future webinars and sessions. I'll be sharing these the links to the replay in the next couple of weeks. Okay, thanks everyone. I really appreciate it. All right. Have a great rest of your day.